So let us consider this reaction. This is OH, COH. What is the name of this compound? This is salicylic acid. Salicylic acid, or it can be called as orthohydroxybenzoic acid. When this is treated with acetic anhydride, CH3, CO, CH3, CO, this is acetic anhydride, right? So what happened here? This hydrogen will leave among a CH3CO group and form a CH3COH. So we can get O, here this one, C double bond O, CH3. Here as usual COO will be there. COH will be there. So this group is called acetyl group, right? CH3CO group is called acetyl group, right? So this is called acetyl salicylic acid. Acetyl salicylic acid. And the commercial name of this compound is aspirin. Right? So this is called acetyl salicylic acid. This is one of the reactions of carboxylic acids. This is a salicylic acid. When salicylic acid reacts with an acetic anhydride, it gives acetyl salicylic acid. This is called aspirin. This is most important reaction. Right. Now, let us check two reactions related to this. One is Kolbe's reaction. Kolbe's reaction. So always when you are writing the Kolbe's reaction, make a mark here in the S or stress S, Kolbe's. So it means that salicylic acid. Got it? It means salicylic acid. That is, salicylic acid is prepared salicylic acid is prepared from phenol. Right. So what we have to be, we should take phenol and we have to add NaOH with that. What is the result here? So the water molecule will be eliminated here and get a sodium phenoxide. O minus will be there. Okay. What it will do that? The oxygen will donate its pair of electron to the ring so that the electrons present here will move to the ortho position. So that we can get double bond O and here the electrons are shifted here. The remaining things are as usual. And now we are adding a CO2 here. CO2 in the sense we know that the carbon is acidic in nature. Carbon is acidic in nature. This carbon is acidic in nature. So it has a need of proton. So what happens here? It takes the electron from here. And by the way, the electron shifts over to the oxygen, which gives rise to the product. Double bond O will be as usual. And here two bonds will be as usual. And here C double bond O negative. Right? And here there will be a hydrogen atom in this space now, right? What this will do, in order to maintain the aromaticity of the benzene ring, it will donate its pair of electrons to the ring. It will donate its pair of electrons to the ring and it releases as H plus ion. So this H plus ion will move on join to the O negative, because this is in need of proton, right? So when this electron shifts over here, the oxygen takes back its electron to maintain the valence. So that again we'll have the aromaticity is restored. Now oxygen again it's had a negative charge, and here in this side the C double bond O and the O has got a proton, right? So then we have to use an acid. This is called acidification. So this acid will go and join with the O minus. So thus gives results. Again OH is retained here and C double bond O, OH is here. So this is called a salicylic acid. Right? This is what salicylic acid, right? So this salicylic acid we are using here. When this salicylic acid is acetylated, it gives acetyl salicylic acid. So that is called as acid. So now we know how to prepare salicylic acid from phenol. It can be asked in a conversion too, right? That is called Kolbe's reaction. Now it's time to know another reaction in which salicylaldehyde is prepared. Do you know what is the structure of salicylaldehyde? Salicylic acid, you know. So here instead of this acid group, if an aldehyde group is present, that is called a salicylaldehyde. Okay, let us go for the second reaction which is related to it. It is called RTR reaction. It is Riemer-Tiemann reaction. So the starting product of Riemer-Tiemann reaction is phenol. So let us take a phenol. This comes under the chemical reactions of phenol, right? Phenol. So this phenol will be treated with NaOH so that it will give a sodium phenoxide ion, O minus Na plus, and this will be treated with chloroform CHCl3, and that will give rise to CCl2OH, and finally this gives a product OHCHO. When treated with NaOH. Again. So this is what will be given in your book. It is a phenol is treated, then it is converted into phenoxide ion, then it is treated with chloroform, which gives CCl2, and that when treated with NaOH, 2 NaOH we can write. That will give salicylaldehyde. But the key is how the CCl3 joined as CCl2 in the benzyl ring. So let us go for the mechanism to understand this. First, let us take the chloroform molecule, that is CHCl3. CHCl3, right? We know that the chlorine is highly electronegative when compared to the hydrogen. So it pulls away this electron towards the chlorine. And this hydrogen is almost ready to leave. So what happened here? The OH from the base will donate its pair of electron here, right, and abstract this proton so that the carbon takes away its electron here. That gives rise to Cl, and carbon has accepted a pair of electron from the bond plus H2 will be removed. Now check out the valency of carbon here. So 1, 2, 3, 4, 5. So it is not possible, na? 5 electrons are there. So in order to cancel this negative charge, what the chlorine will do? The chlorine will take away its electron and will move a Cl minus. So that it will be generally rated here. We can get C with with the lone pair of electrons along with the 2 chlorine. This is called, and plus Cl minus will be moved on. Cl minus will be there, right? Cl minus will be moving on. Right, this This part is called dichlorocarbon. Dichlorocarbon. Dichlorocarbon, right? Here, whether the octet of the carbon is fulfilled, 2 electrons here, 2 electrons here, 2 electrons here, no. So it is in need of 2 more electrons. So now it will act as a Lewis acid. Lewis acid to accept a pair of electrons. Got it? To accept a pair of electrons. So this is dichlorocarbon. Let it be here. Now we can move to the next part. As usual, phenol is taken. Phenol is treated with NaOH. As usual, we can get O minus, right? Phenoxide ion. Let me write in bonds to show the resonance. The same phenoxide I am writing here. O minus. So the O minus will donate its electron here, and this bond will shift over here. This gives rise to double bond. Sorry, again not bond here. Here no bond here. Here is a negative charge and 2 bonds are here, and this is double bond. Right? Here there is a pair of electrons. Now this dichlorocarbon needs a pair of electrons. So what it will do? This will give its pair of electrons to the dichlorocarbon and attaches here. This will give rise to a compound like double bond O. 2 bonds will be here, and here what happened? C along with Cl2. Here the carbon has accepted a pair of electrons here, so that acquires a negative charge. And there will be a proton at this benzene ring in this place. So the proton will donate a pair of electrons to the benzene ring. And meanwhile the oxygen will take its electron away. This proton is released as H plus ion, which goes and attaches to the negative charge of the carbon. Like this. That gives rise to the product. That gives rise to the product. O minus again. And here we will have CH and 2Cl. Right. At this time, the NaOH is employed. 2 sodium hydroxide molecule is employed here. What happens that the 2 Na and these 2 Cl will leaves away, and the nucleophilic substitution reacts takes place, and these 2 OH minus ion will be substitute these chlorine ions. So we can get a compound like this, O minus, and here carbon, hydrogen is here, and here instead of these 2 chlorines, 2 OH minus ion get substituted, right? And this is highly unstable position, so that a water molecule can be easily eliminated from here. So that we can get a compound O minus, and here CH double bond. Got it? That's it. And finally, acidification of this compound. Treated with an acid, it go and reacts with this O minus, so that we can get the final product as OH CHO. Salicylaldehyde. So this is called a salicylaldehyde. And we can understand that there will be a hydrogen bonding between the oxygen and hydrogen of this compound, so that orthoisomer is highly preferred. Right? So here, this compound is otherwise called as orthohydroxybenzaldehyde or salicylaldehyde. Orthohydroxybenzaldehyde. Benzaldehyde or salicylaldehyde.